Hey there, Haxers. OP Haxer here. We're committed to providing understandable computer science tutorials. Today we'll be using recursion and depth-first search to find the solution of LeetCode problem 236, lowest common ancestor of a binary tree. Let's begin. Okay, so let's just read the problem statement here. Given a binary tree, find the lowest common ancestor, or LCA, of two given nodes in the tree. According to the definition of LCA on Wikipedia, the lowest common ancestor is defined between two nodes P and Q as the lowest node in T that has both P and Q as descendants, where we allow a node to be a descendant of itself. Going through example 1 here, the input is a binary tree in array form. And if you haven't seen this before, this form right here and this over here are equivalent. So the order goes top down, left to right. So 3, 5, 1, 6, 2, 0, 8, null, null, which just means empty, 7, 4. Let's go up here. 3, 5, 1, 6, 2, 0, 8, null, null, empty, empty, 7, 4. And yeah, these two forms are equivalent, top down, left to right. P equals 5, Q equals 1, so those are the two vertices that we're trying to find the lowest common ancestor of, and we assume the constraints of the problem show that P will not equal Q. And we can see the output is 3 for example 1, because the lowest common ancestor of 5 and 1 is 3. Looking at example 2 here, the input is still in the same format and it's also the same exact tree. Okay, and now we're looking for 5 and 4. 5 and 4. So we're looking for this one and we're looking for this one here. And the lowest common ancestor of 5 and 4 is 5 itself. And this is because a node can be a descendant of itself according to the LCA definition. In other words, a node can be its own ancestor. Don't ask me how that makes sense logically, because we don't really see that in the real world. Like, you can't be your own parent, but according to the definition of an LCA, I guess according to Wikipedia and just the common agreement in computer science theory dealing with trees, the lowest common ancestor allows a node to be its own ancestor. So 5 is its own ancestor here, and then we only have to worry about whether the left subtree or the right subtree contains 4. We'll do a recursive call, we'll check the left subtree, and we can see, okay, it doesn't contain 4. How about the right subtree? Yes, the recursive call will return true because we see a 4 down here. So that means the lowest common ancestor of 5 and 4 is 5. And 3 is also a common ancestor of 5 and 4, right? But it's not the lowest common ancestor, right? The lowest is going down this tree, just going down to the deepest level. The lowest level down is going to be 5. And so I hope that makes sense. Okay, so let's take a look at our code here. And this in comments shows the basic Java class that is used to represent a tree node. And it's just a public class tree node. It has a single int value, and it has a left and right tree nodes as its attributes. And this is just a constructor that takes the value of the tree node. Okay, so let's go through this code line by line. So we have our lowest common ancestor here, right? That's just the function header. Takes a tree node, root, tree node P and Q. And then if root equals null, or root equals P, or root equals 2, return root. So this is what you call the base case of recursive call. It's one of the base cases of a recursive call. Whenever you see a return, that means that's where the recursive call ends. We have 4 return statements here. just ignore this. This is equivalent to this last line here, and I'll get to that later. And that's just a more condensed form of, instead of writing 8 lines, you could just write this 1 line. So basically, if root equals null here, that means we've reached the bottom of a tree, and 7 doesn't have any kids, so that means we reach this area down here. And basically that's what root equals null means, is that if we go down here, we've reached an empty space. If root equals p or root equals q, return root, and that means in our example 2 here, our root is p, our root is 5. So when we reach the case that the root of this subtree, right, this subtree that starts from 5, if the root of that subtree is one of the nodes p or q that we're looking for, then we can just return that root of that subtree as a lowest common ancestor. And this is the case because once you have that root being one of the values that we're looking for, we can't go any lower than that. If we go past 5 here, we just can't go any lower because we're assuming, according to the constraints, that there are no repeat values. All node values are unique, so there are no repeat values. According to that constraint, once you go below the root of this subtree in these left and right subtrees, you're not going to find another 5. You're not going to find a lower subtree past this 5 that contains 5 and 4, since all the node values are unique. So that's why once you reach a subtree root that contains p or q, you can just return that root. So I'm just going to write that out for you here in the comments, just in plain English, so it'll make sense intuitively. So if the root of the current subtree is null, or the root i.e. we have reached the bottom of the tree. Just a second here. And or if the root of the current subtree is one of the, is either p or q. So if the root of the current subtree is null, i.e. we have reached the bottom of the tree, that's when we do a recursive call on the left and right subtrees of 7 here, and they're both going to return null because there's nothing there. And or if the root of the current subtree is either p or q. So basically, if this root of this current subtree is p equals 5, then we're going to return vertex 5 as the lowest common ancestor. So if this condition is not immediately satisfied, we do the recursive call on the left and the right subtrees. And so if we do the recursive call starting from the root of the entire tree, which is 3, is root equals null? No. Does 3 equal 5? No. Does 3 equal q, which is 4? No. Okay, then we have to keep going. So we do a recursive call lowest common ancestor on the left and right subtrees. A recursive function is a function that calls itself, right? So we have lowest common ancestor here, and within that function we are calling itself. And the reason that this doesn't continue ad infinitum is that we have base conditions that tell the recursion to stop. So that's every time you see a return statement in a recursive function, that tells you, okay, this is where you stop. So we have 2 return statements here. Okay, so if we start from 3 here and we do the lowest common ancestor of left, this is gonna zoom down into this next level, this left subtree, as a new call stack. And this is the current recursive level that you need to focus on, is everything from 5 starting down. And we know when we call lowest common ancestor here, we're gonna get 5 and 4 paired together, and then since this 5 fulfills this condition where root equals p, which is 5, we return 5. So yeah, tree node left is going to end up being 5, and then we're going to shoot back up here to the top of the tree 3, and then we're going to call this next recursive call lowest common ancestor on the right subtree, and then this 1 becomes the root of the subtree under consideration. Is 1 equal to P or Q or null? No, that's not true, so we keep going. So we do a recursive call on left and right subtree, so on 0 and 8. Is 0 equal to null or equal to 5 or 4? No. So this is not fulfilled, so then we do a recursive call on the left and right, and then basically we're going to do lowest common ancestor of null and null. Root.left is null, root.right is null, and at that level that's going to fulfill this condition. If root equals null, return the root. So this is going to return null, null, and this is going to return null back up to the 1 here. So now we're back at the 1 level, and this tree node left is going to equal null, and then 1 is going to call tree node right equals lowest common ancestor of root.right, which is 8, and the same thing is going to happen, right? So we're going to go back up here. Now 8 is the current node under consideration, and does 8 equal null? No. Does 8 equal 5 or 4? No. So we keep going. So we do a recursive call on left and right, and the left and right subtrees of 8 are empty spaces, basically null. So when we go into this recursive call and the current root under consideration is null, we're going to return null. So left and right is going to return null when we're at the vertex 8 call stack, and then we're going to go is left equal null, then return. Basically these two statements here are equivalent. This accounts for the fact when we have found a lowest common ancestor, and it also accounts for the fact when we haven't found a lowest common ancestor and the return value is just null. So if the left side return null, then return the right. Consider this call stack from vertex 1. The left recursive call is going to return null. The right recursive call is going to return null. The left and right recursive calls of 0 return null, null. The left and right recursive calls of 8 return null, null. And 1 is going to also return null. And then now we're back at the vertex 3 recursive level, and it's going to say if left equals null, which is not true, then let's read it in this form here, right? I'll uncomment this so you can see it better. If left equals null, return right. Else, if right equals null, return left. But that's just where we return left, which is 5. We return the value of the left recursive call from the root 3. So the reason why this works as a final statement is that, okay, so let's refer to our OPAXR article here. If the left lowest common ancestor returns null, then the right subtree must contain the lowest common ancestor. Likewise, if the right lowest common ancestor recursive call returns null, then the left subtree must contain the lowest common ancestor. If the left and right lowest common ancestor recursive calls both return null, then the root of the current subtree is the lowest common ancestor. Let's see why this is true. So if the left recursive call returns null, let's consider this case because it applies to example 2. If the right recursive call returns null, then the left subtree must contain the lowest common ancestor. So we did the right recursive call here starting from 3, and that returned null. And so that means then we consider the case if the left recursive call returned not null, so it returned a tree node value, that means that must be the lowest common ancestor. And the last case, if the left and right recursive calls are both null, then that only leaves us as the root, as the lowest common ancestor. And this last line here, line 18, is actually equivalent to all of these lines, but it's condensed in a single form. This is called a ternary operator, where you can put an if-else statement within one line, and this is actually an if-else statement nested within an if-else statement, and so that's why we can actually nest a ternary operator within another ternary operator. So look up ternary operators. It's kind of hard to explain, but for those who have seen ternary operators before, you'll see that this statement here is equivalent to this one. Yeah, it reads, if left equals null, then return right. That's what's going on here. This colon represents the else, and then that puts us down here. If right equals null, then return left. That's what we got here. Else return root, and the colon is the else return root. So if you haven't seen ternary operators before, just ignore that line and just write this one instead. I like to have very lean code, so I like to condense things where I can. So hopefully that makes sense. Okay, so let's run our code. This is recursive DFS. Okay, so we beat 100% of solutions. Recursive DFS is usually the fastest way to approach any tree problem in general, in most cases. If not all cases, but definitely most cases. Okay, thanks very much for tuning in. Be sure to like, comment, and subscribe, and visit our blog website at ophaxer.com. We post all our solutions on the blog, and yeah, we'll see you guys soon again. Ophaxer out.